Welcome back to linear algebra. In this video, we're going to be talking about matrix algebra. The idea here is that just like we did with vectors, I want to look at the rules we've established for performing operations on matrices and see what kind of properties we can establish about those rules. Before we can do that, though, I do need to establish a little bit more vocabulary, so let me get my head out of the way. And let's put down a formal definition for equality on matrices. It's going to be something that probably makes sense. You probably could have figured it out on your own. But formally speaking, if we say that two matrices are equal, if and only if the matrices have the same dimension and each pair of corresponding entries are equal. All right, matching up corresponding entries, that's how you show that vectors are equal as well. So nothing crazy going on there. Making sure that we have the same dimension ensures that each entry of one matrix has a corresponding entry in the other matrix. All right. And a lot of what we're going to be looking at is proving that matrices are equal in certain circumstances. So that's definitely going to be something that we need to worry about. A square matrix is a matrix which has an equal number of rows and columns. Typically, we're going to talk about a square matrix being an n by n matrix. And for purposes of the next definition, it is worth taking the time to write out an n by n matrix A, which has entries A11, A12, down through to A1n, A21, A22, down through to A2n, all the way down to AN1, AN2, and all the way over to ANN. The main diagonal of a square matrix is the collection of AII entries. So A11, A22, A33, and onward down to ANN. Moving in that orientation along the matrix. We call that the main diagonal of the matrix. It is diagonal. It is going to be the one that we are going to ascribe a number of properties to, most of which actually come out of one particular matrix. the n by n identity matrix, which is written as I sub n, or when the dimension of it doesn't really matter, we'll often omit that and just call it I, because lazy and why write more when less will do. But the identity matrix, In, has 1 for each entry on the main diagonal, and 0 for each other entry. And there's some really nifty properties of the identity matrix that we'll be talking about in just a few moments. But as a simple example, I3 is going to be the matrix, again, 1s on the main diagonal and 0s everywhere else. 1 0 0 0 1 0 0 0 1 is the I3 identity matrix. The property that I want to immediately call to your attention about the identity matrix is if you take the columns of the matrix, you get the standard unit vectors for Rn, right? In this case, the identity matrix I3 has the 3 standard unit vectors in R3. The identity matrix in 5 dimensions, I5, has the 5 standard unit vectors for R5, and so on. All right. That is a property. We could prove it, but it basically follows directly from the definition. The kth column is going to have a 1 in the kth entry and a 0 everywhere else. That's the definition of the identity matrix. So I'm not going to take the time to prove that, but I do like mentioning it. It's an interesting thing that we can talk about. All right, the last matrix I want to talk about is the m by n 0 matrix. And here is where my terrible handwriting really comes into play. But it's not like when this is typed up, it's that much easier to decipher. The 0 matrix is represented using the letter capital O. All right, so the matrix represented with capital letter O has the entry 0 in every entry in the matrix. And we can have a 0 matrix in any kind of dimension. So 0 sub n again, it's just zeros everywhere, just a whole bunch of zeros. All right. With that little bit of extra vocabulary, we have enough to dive into the properties of algebra for matrices. All right. So my theorem here on properties of matrix arithmetic, I need several assumptions. I need 3 matrices, A, B, and C. And I want to assume that they are sized, they have the dimensions necessary so that all the operations are defined. If I want to add some matrices together, I'm going to assume that they have the same dimension. If I want to multiply some matrices, I'm going to assume that the number of rows and columns match up the way they need to. P and Q are both going to be scalars. I will use the letter O for the zero matrix, the letter I for the identity matrix, again, such that everything is set up where it works. The dimensions of the zero matrix and the identity matrix, however they work out so you can actually perform the calculation. Right. The first four properties, very straightforward. These are same properties you see on arithmetic on real numbers: the commutative, associative, identity, and inverse properties of real numbers, of real number addition, of real number multiplication. They are the same properties for matrix addition, and they all work, which is fantastic. Then we've got a couple of distributive properties. We can distribute scalar addition or scalar multiplication over matrix addition. And we can distribute scalar multiplication over the addition of scalars. All right, those are both the distributive property. Then we've got that rearranging between scalar multiplication and multiplication of a scalar, which is a kind of associative property, will work. And we've got the scalar 1 multiplied by any matrix is equal to that matrix. These 8 properties in total should look very familiar to you. We went through practically the same list when we looked at the properties of vectors in the first place. The next set of properties is a little bit harder to deal with. The next set of properties is going to deal with matrix multiplication, where we are still going to have an associative property, even if we don't have a commutative property. And we will have a distributive property. We have to set up the distributive property in both directions, because unlike the distributive property for real numbers, right, multiplying on the left and multiplying on the right are different things for multiplying matrices. Right, but we can still call both of those distributive properties. And then we have some properties of multiplication, matrix multiplication and scalar multiplication, where we can move the scalar multiplication into multiplying in any place. We can wait until after we're done with the matrix multiplication. We can multiply the first matrix. We can multiply the second matrix. I guess that this is an associative property, but just like the associative property up above, I'm kind of going to put an asterisk on it because it's a little bit weird. All right. And then finally, the reason that the identity matrix is so interesting is that multiplying the identity matrix times A in either direction gives you matrix A. I am definitely going to come back and look at this property because it's a little bit weird. Um, I'm not going to have the time, I'm not going to try to have the time to prove all of these properties, but I do want to prove a couple of them to give you a feel for how we would go about doing that. That last one I do want to mention, we're really going to spend some time talking about because it is weird. But we have the 8 properties of matrices that kind of look like the properties of vectors, and then 5 more properties of matrices that have to do with matrix multiplication. Um, Matrix multiplication is based on the dot product, but at the same time, it's very different from the dot product. So the definitions here are quite a bit different than the definitions we had or the properties we had for dealing with the dot product. But let's take a look at one of the earlier properties. I like thinking about the 1 and -1 and how those things work. So let's take a look at those two to start off with, and then we'll come back and we'll look at a couple of the others. All right, but for matrix A, which has entries A11, A12, A1M, AN1, AN2, ANM. We can think about 1A is 1 times that matrix, and the rule of scalar multiplication says multiply each entry in turn. And 1 times anything is that thing. So 1 times A definitely brings us back to A. And if we think about A plus the opposite of A, we can think about opposite the same way we think about opposite on real numbers. And this is A plus -1 times A. So A is still A11 to A1N, AM1, AMN, and -1 times A is going to be negative A11 through to negative A1N, negative AM1, negative AMN. And if we want to add component by component, that's A11 minus A11. A12 minus A12 all the way through to A1n minus A1n, A21 minus A21 all the way down to AM1 minus AM1, and all the way down to AMN minus AMN. In every single case, you have the same thing subtracted from itself, so we get the matrix that is 0 everywhere. That is the 0 matrix. So we get that nice proof on at least those two properties. All right. To choose one of the properties on matrix multiplication as a warm-up, let's consider the distributive property. And working with this is a little bit messier. As I've said in a previous video, we want to start thinking about matrices a little bit more abstractly. So I want to define A as a collection of row vectors. Row vector A1, row vector A2, down through to row vector AM. And then B and C, I'm going to define as a collection of column vectors. So matrix B has columns B1, B2, down through to Bn, and C has vectors C1, C2, down through to Cn. Right? B and C have to have the same number of columns, otherwise this bit of addition wouldn't be defined. And the vectors A, B, and C, all of them have to have the same number of entries, otherwise the multiplication wouldn't be defined. So all of the A vectors, all of the B vectors, all of the C vectors are all in some p-dimensional vector space. I don't know what p is. I don't really care. The thing that is important is that they are all the same. But with that established for us, then we can start looking at some more specifics. Well, I know that B plus C, we're going to add entry by entry. But if we add all the entries in the first column of B plus all the entries in the first column of C, we'll get the same thing we get if we add the vectors B1 and C1. That's true all the way down the line. And if I want to multiply A times B plus C, well, multiplying matrices is a series of dot products. The rows of A dotted with the columns of B plus C. So we will have the first row of A dotted with, it helps to put this in a matrix, the first row of A dotted with B1 plus C1. the first row of A dotted with B2 plus C2 all the way down to the first row of A dotted with Bn plus Cn. And we'll continue that for every row until we get down to the bottom. The mth row of A dotted with B1 plus C1. The mth row of A dotted with B2 plus C2. And then continuing down until we get the mth row of A dotted with Bn plus Cn. That's probably the confusing one to think about. It's a little bit easier to think about what would happen if we just want A times B. Each entry is going to be the ith row of A multiplied by the jth column of B, doing a bunch of dot products. And if we multiply AC, we'll get the same thing. You could write it out in longhand like we did on the first one, but at this point, now that you see what the structure is, I think condensing it is going to make our lives easier, because what we were really looking at is AB plus AC, which is AI dot BJ plus AI dot CJ for each entry. And we know from properties of the dot product that I can factor out that AI add the vectors bj and cj first, and then do the dot product. And that's exactly what I wrote in long form as A times B plus C. Great. That takes care of everything I wanted to talk about, except for those properties of the identity matrix. And here's where I'm going to make you do a lot of the thinking. Instead of going through and trying to prove that, I want to look at a specific matrix. One, 3, 2, 4, -1, 5. And I want to just go through the calculations. If I want to multiply A times I will take 1, 3, 2, 4, -1, 5. Now to multiply a vector or a matrix with 2 rows and 3 columns, we need to multiply that times matrix I that has 3 rows. And of course, matrix I is always a square matrix, so the number of rows and the number of columns is going to be the same. And then let's just go through and see what happens. First row, dot with first column. 1 times 1 is 1. 3 times 0 is 0. 2 times 0 is 0. Then first row, dot with second column. 1 times 0. 3 times 1 2 times 0. There's a lot of 0 that goes on here. That's why this works out. First row dot with third column. 0, 0, 2. Second row, 4, 0, 0, 0, negative 1, 0, 0, 0, 5. Adding 0 to things is really easy. Getting out what we expected to get out is very nice. Now, if I want to set this up in the other order, that means I need my identity matrix to come first. Remember, the number of columns in the first matrix has to match the number of rows in the second matrix. Matrix A has 2 rows. So this time I need the 2 by 2 identity matrix, 1, 0, 0, 1, to multiply by the matrix 1, 3, 2, 4, negative 1, 5. But then when we go through, we find that it still works very nicely. First row, first column. 1 times 1, 0 times 4. 1 plus 0 is 1. First row, second column, 3 plus 0 is 3. First row, third column, 2 plus 0 is 2. Second row, first column, 0 plus 4 is 4. 0 plus negative 1 is negative 1. 0 plus 5 is 5. And we once again get everything to work out. All right. I would like you to think about how you might establish this proof. For any 2 by 3 matrix A, I want to prove that A times I is equal to A and that I times A is equal to A. All right. Compared to the proof that I went through, notice that we're not doing this in general. I'm just doing this for 2 by 3 matrices. So we're looking at what we just did and we're generalizing it and we're trying to make sure that that makes sense. If you can get that much, then we're well on our way to going through things. Take a few minutes, see what you can do with that, and I'll see you in the next video.